We're going to focus our attention on Thompson's cathode ray tube experiment, which really led to two things: the discovery of the electron and some quantitative information about the characteristics of the electron. So the essence of the cathode ray tube experiment can kind of be demonstrated in these two animations here. You can see the one on the left here shows kind of a basic operation. So cathode ray refers to basically a series of electrons that are ejected or accelerated across a voltage in here. And as those electrons travel through this region, they were subjected to, as you can see here, an electric field. So you can see how the electric field is switching here between positive on top, negative on the bottom, which bends the charges one way, as predicted. If you understand that these are electrons, then you understand that they will bend different ways depending on the direction of the electric field. This animation over here really just kind of shows that it was not as simple as one or the other. We can vary, using this control here, we can vary the strength of the electric field, and by doing that we can vary the force acting on the particles and bend them in a more pronounced way. So really, this experiment demonstrated that there are electrons, and that's demonstrated over here because you have created some sort of source of electrons. So somehow you're stripping away electrons from some sort of material over here and causing them to travel in this direction. So we see that there is evidence for something smaller than an atom. And then we can start to play around with things like electric fields in order to get some sense of the charge on these things. Now we know the charge on electron is negative, so this is, the outcome is predictable. But when Thomson performed this experiment, first thing he did was subject these electrons to positives and negative fields to see which way they bent. Then he could draw the conclusion that electrons are negative. But that wasn't enough. Thomson wanted to find a little bit more about the amount of charge, or, a lot of quantitative things. If you ask yourself, well, I just discovered a particle, what do I want to know about that particle? You might want to know the charge, it's negative. You might not want to know the magnitude of the charge. You might want to know how much does that particle weigh. So Thomson developed a series of steps in order to deduce these things. So on the one hand, let's just understand what we have going on here. We have a series of electrons that are built up on this plate, and when there's enough voltage, they will begin to accelerate from one side to the other in essentially a straight line. Even though I didn't draw it nice and straight, they will travel from one side to the other. That's what electrons do. They will travel from a negative place to a positive place. Now, the first thing that Thomson did was he subjected these electrons to a electric field. And I'm going to create an electric field by putting two charged plates, one on the top, one on the bottom. And let's charge those plates. Let's say the top one got charged negatively and the bottom one got charged positively. You'll recall what that creates is a uniform electric field in this region. I'm not going to draw it because I don't want to mess things up too much, but the electric field in this region will be from the positive to the negative plate. If we simply did that, then any electrons that were ejected from this plate here would be attracted to the positive side and repelled by the negative side, and they would bend in this downward direction. So there would be a force acting on each and every one of these electrons that are coming out of here, and that would cause them to travel in a downward direction or be bent in a downward direction. Now, Thomson developed an idea, and I'll show you the math around it, but he also made sure that he had the opportunity to put a magnetic field in here as well. And if you do it right, you can create a magnetic field in this region. I'll just draw a series of circles showing the vector direction, and we're going to say the magnetic field is out of the page, signified by these circles with dots on them. You'll recall that's how we show a magnetic field out of the page. All right, so if you do this, an electron that enters this region, let's do our electrons in purple, an electron in this region traveling with a certain speed will now feel two forces. It will be feeling a force due to the electric field strength in this region. So there'll be electric force in the downward direction. And going back in your memory banks, because of the hand rules, there will be a magnetic force on this as well. And the magnetic force, check for yourself, hand rule will tell us the magnetic force will be in the upward direction. So you can imagine that depending on which one wins in this little tug of war of electric forces trying to pull this thing down, magnetic forces trying to pull it up. And by the way, it doesn't have to be up, down. It could be left, right. We don't know how this thing's oriented, but the electric field is in this direction. The electric force, pardon me, is in this direction. And if we do this just right, you will see that we can manipulate the electric and magnetic force in such a way that instead of bending up or down, this thing can travel in a straight line again. So understand this scenario, understand that Thomson created this situation. And again, his purpose here was to try to investigate the nature of the electron, find out something about its charge or mass or anything else that he can find out about. Now, where it really gets ingenious is the math. So the first thing mathematically that Thomson did was he created a situation that we described towards the end of the last slide where he balanced the electric and the magnetic forces acting on the electron. In other words, the electron was traveling in a certain direction, and he made sure that he manipulated his magnetic force in one direction, his electric force in the other direction, and when he did that, he could say safely mathematically, and he didn't have to do, it wasn't very tricky because he just had to play around with those magnetic and electric forces to the point that the electrons traveled in a straight line. So once he saw that, he knew he had those forces balanced. So now he can say mathematically that the magnetic force is equal to the electric force. Now, we're not too worried about direction. We just know that they are equal and opposite to each other. Now we're going to go back in our previous studies and remember the magnetic force on a charge moving through a magnetic field is equal to Q times V times B. And again, going back a few chapters, the electric force is going to be Q times the electric field strength. So QVB equals Q times E. You can see that we can quickly eliminate the charge. It's on both sides, multiplied by everything. And for reasons that will become clearer shortly, I'm going to rearrange this and say that the speed of this electron moving through the electric and magnetic fields is going to be equal to the electric field strength divided by the magnetic field strength. All right, this is step one. And now I'm going to tell you why we need step one, because the speed of the electron was something that is not easily observed or easily measured. And so the first step allowed Thomson to figure out the speed of the electron before he moves on to step two. So pretty simple experiment, but very effective at finding the speed of the electron. Now, step two, bending the electrons with the magnetic force. Why? Well, it will become clear in a second. So, in other words, he turned off whatever was creating the electric field. So we no longer have an electric field. In other words, now this electron is moving simply through a magnetic field, so it's got a certain velocity, moving through a magnetic field, causing a magnetic force in a direction that is perpendicular to the velocity. And that results in circular motion. All right, so now this electron travels in the path of a circle. Now, watch what that allowed Thomson to do. We now have a situation where the magnetic force is the only force acting on the object, and it is causing centripetal motion. So the magnetic force is the circular force. And you've seen this before as well. The Q times V times B is going to be equal to the Q, sorry, not Q, is going to be equal to the mv squared over r. mv squared over r. And now there are two things in here that Thomson and everybody at the time, nobody knew two of these things. One is they did not know the charge on an electron, and they didn't know the mass of the electron. But they did know, because of the first step, oh, and by the way, we can get rid of one of these speeds here and one of these speeds here. They did know the magnetic field in this region. They did know the speed, and they did know the radius. So, step short of finding out exactly what he was seeking, he would like to know the charge or the mass, but all Thomson really could do was find the charge to mass ratio for electrons. And the charge to mass ratio can be found by taking V over BR. And again, we know these three things. Because of step one, we know what V is. We know the magnetic field because that's part of the experiment that we're creating. And we can measure and observe the radius that the path of the electrons travels. So again, would have been great for Thomson to know the charge or the mass, but all he could do is give you the charge to mass ratio, which for a number of years was actually really good for chemists and physicists to do further studies. And in fact, the charge to mass ratio turns out to be a pretty characteristic thing for all kinds of different subatomic particles. The charge to mass ratio of an electron is unique and different than, say, the charge to mass ratio of a proton. If you have an ion, it will have a unique charge to mass ratio. So in a lot of ways, this wasn't really a failure. It was a bit of a shortcoming, but it did allow progress in the fields of chemistry and physics. All right, let's take a look at an example. So we have a description here, a beam of ions. Changing gears a little bit, it's not electrons, but as you'll see, the math really turns out to be exactly the same. So we have a beam of electrons traveling in a straight line when fired through perpendicular electric and magnetic fields. I'm going to draw this again in a real cartoon form. So we have an electron that's going to be traveling through a region in space that has our classic parallel plates here. We'll put the negative on top and the positive on the bottom. And then it also has a magnetic field. I'll draw the magnetic field here as well. Just to have a real good visual, I think it's important to study this situation. And when we do that, and we have it set up just right, the electrons travel undeflected straight through here. So they say straight line, you'll hear a lot of questions say undeflected. And the reason that happens is because we have the classic, hey, there's a force in one direction, a force in the other direction, but the two forces are the same. And that is important because that allows us to do, you know, your first calculation, or what I called step one in Thomson's experiment, to be able to say, start with this underlying big idea that the magnetic force and the electric force are the same when we do this. So in step one, magnetic and electric forces are balanced, they're equal and opposite. So we can just say their magnitudes are the same. Now, we'll develop a formula specific for this case. QBB is equal to Q times E, and we'll see that the two charges cancel out, and we will find the speed. You might say, well, we don't need to know the speed. Well, you do in order to do the next step, so trust me, let's find the speed to start with. So the speed should be the electric field divided by the magnetic field strength. The electric field in this question is 2 times 10 to the 6, so 2.0 times 10 to the 6 volts per meter. And the magnetic field is 2.0 Teslas. And so our speed in this case is 1.0 times 10 to the 6 meters per second. So there's step one, finding out the speed. Why do we need step one? Well, it's really so that we can go on to step two. And that was this second part that describes when the electric field is turned off, the ions then travel in a circular path with a known radius. So we want to know the charge to mass ratio. Step 2 is going to do it for us. Step 2, we have the electric force. No, we have the magnetic force equal to the circular motion force. We have the Q times V equaling the mv squared over r. Simplify a little bit, get rid of one of these speeds, and now we have charge to mass ratio being equal to V over BR. 1.0 times 10 to the 6th meters per second divided by magnetic field of 2.0 Teslas and radius of 0.01 meters once we convert to meters. And so in the end, we get a charge to mass ratio of 5.0 times 10 to the power of 7. And the units, now if you try and keep track, you're going to get meters canceling with meters. You're going to get like per second Teslas, but it's maybe easier to take a look at the units of charge over mass. If we worked with all our fundamental units, which we did, we should get a unit, which is the charge in coulombs over the mass in kilograms. So this ion has 5.0 times 10 to the 7 coulombs worth of charge in every kilogram of the ion we're using. So this is kind of a typical example. We got away from electrons, but certainly we can go back to electrons and do some calculations involving those. But it's really this two-step process, this relationship between what was happening when we had balanced forces versus what happened when we had an unbalanced force and an accelerated motion, like the centripetal force, circular motion. And this is the typical way that Thompson's experiment questions tend to look, although they can be a little more simple in some cases. They can be a little more complex, as we're going to see, because really, Thompson's experiment was a precursor to a modern day device that's used in analytical chemistry that we're going to study next, and it's called a spectrometer. So if you understand this rudimentary experiment, how Thomson used this experiment, first of all, historically to prove that there were electrons, so his device stripped electrons off of atoms, showing that the atom wasn't indivisible. Secondly, how he could quantify and calculate information about the electrons or any particle we put in this kind of situation using this kind of two steps where if we don't know enough information, we just equate certain equations so that we can simplify them and solve for different pieces of information. If you understand Thomson's approach, then understanding a spectrometer will become very easy. Key thing here is no, in my mind, new physics, right? We've seen balanced forces before in Physics 20. We've seen magnetic forces and electric forces before in previous chapters this year. And we've seen situations where we did this on their own, where we took a magnetic force and caused circular motion in a charged particle. We got hand rules going on. We got directions of electric forces and magnetic forces. So while there's a lot of elements to these questions, nothing here is new. It's all review of previous studies.